All right, here we go, function folks. Finally, the last lesson of this huge long chapter on polynomial functions and equations and inequalities. Um, what's nice about today, it's kind of a review lesson. We've done rate of change before. Rate of change shows up in just about every unit in the whole chapter, or the whole course rather. And we'll see that we add little twists on it as we go. But it's really this no new topics today, I would say, which is kind of nice. The 3-minute review is from a handout. This is actually example 2, but just to get our brains firing in the right spot, we're gonna do this one before our example 1. So we're asked to calculate the rate of change over that interval. X is 2 to X is 5, and essentially this is boring old AROC calculation, right? Average rate of change is just going to be f at x2 subtract f at x1 over x2 minus x1, and it slope, right? Average rate of change is the slope over that interval. And what do we got? We got f at 5 is just -3 times 5 minus 3 cubed plus 3, and that is -21. F at 2 is, excuse me, clunk that into your calculator, 6. So I get, this is F at, I'm going to do an extra step here just so we can see what's going on. 5 minus 2, and so that is -21 minus 6 over 3 is -27 divided by 3, -9. So that means from 2 to 5, the function is decreasing, right? It's going downhill. The slope of the secant is -9. IROC, an estimate for the instantaneous rate of change. Remember, is this idea, and we did sort of, when we first tackled it, we do several calculations where, we do an instantaneous rate of change over a smaller and smaller interval where my x1 and my x2 got closer and closer together, right? Where I go from 4.5 to 4.1 to 4.01 and so on, and I look for the pattern. Um, we're, we've done quite a few of these calculations, right? We want, if we think of x1 being 4, then we want x2 to get close to 4, but we will actually still want to have a calculation. So we pick it as close as we possibly can without getting too frustrated about typing too many decimals in our calculator. So usually I like using the 4.01. The 0.1 is pretty close, so I'm going to use that interval. And I get f at 4 is, plunk that into your calculator. That one happens to be 0. Wow. And 4.01 is negative, it's going to be close to 0, right? Negative 0.90903 when I jam that into my calculator. And so I get, with all the decimal places, or is this approximate? I rounded. So this is going to be rounded off too. This is 0.090903 subtract 0 over 4.01 subtract 4 is 0.01. And I get, when I divide that, that's going to be around negative 9.0903. And remember, the idea here is that if we were to use another decimal place, 0.001 or 0.0001, then it'd be an even better estimate for the instantaneous rate of change. Well, what is that getting close to? Probably it's getting close to -9. So it appears, and this is only one calculation, but we're, you know, we've done enough of these to sort of see the pattern. It appears that the IROC at x equals 4 is -9. That's what it appears. And notice when we first did IROC, we talked about there was different ways of doing instantaneous rate of change estimates. There was the preceding interval, there was the following interval, and the centered interval. And we only did one calculation, right? And each of these we can sort of start wide and get more narrow. Which one did we do here? Did we do preceding, following, or centered? Well, since this is the value that we wanted, and our other x value was a little bit bigger, that's following, right? So we wanted to go a little bit we had our interval was a little bit after the point we were interested in, so it was a following. What would a preceding look like? This would be f at 4 subtract f at 3.99999, whatever, right? Dandy. Before I get to the graph, I want to mention something here. See, we show these calculations on a sketch. That'll be good review. I want to mention something that we always end up with an expression like this, with a little tiny number, and in fact, that's how far we went away from the value that we wanted to find the instantaneous rate of change. This is kind of like the difference, right? This is how close the 2 points are from getting close to each other. So we'll see soon that this graph is some sort of cubic, right? Wow. And in fact, we'll be able to graph this one exactly because we know what this cubic looks like. But what we're talking about here is our x1 and our x2 getting closer together, right? Where this interval is getting smaller and smaller. This was the 0.01. And in fact, one way to think of this, and I'm going to change my color here, is I'm not even going to think of it as 2 points. I'm going to think of my x1 as just a value, and my second value is some interval away that I'll call h, and I want h to get as small as possible. So let me show you what I'm talking about. I could think of, instead of x2 and x1, I could think of my IROC, and you're welcome to write this down. We'll actually see it in action again during example 3, that f at x plus h, my x2 is kind of like x plus h, where h is this small little interval. Subtract f at x all over this little value h. And we want h to get as small as possible, right? That's the very same thing as this one that we used as the average rate of change, but in this case, we want the interval h to get as small as possible. And notice that this again is a following. This is a following interval. And I could, though, think of this as a preceding interval, right? Let me have another go here. Where if this is the value that I'm interested in, and I want h, the interval where my other value is, to be as small as possible, then what's this going to be? Well, this is going to be x minus h, isn't it? And then I want my IROC calculation would be f at x subtract f at x minus h all over h. And that's still the slope, right? That's still the slope of the tangent as h gets smaller and smaller. All right, keep that in the back of your brain. We'll actually see these formulas in action in example 3. Now we want to get to drawing these things on the sketch. Remember that instantaneous and average rate of change also means something as far as a graph is concerned. All right, and I'm going to have a bit of a weird scale here, okay? I hope you don't mind. And this has been stretched, so I'm actually going to go up by 3 each time. I hope that's okay. That's 3, 6, 9, and so on. And so my parent function of this sketch, and this is good review because we got a test coming up soon, right? The parent function goes through 1, 1, but then if I stretch it and flip it, then instead of 1, 1, it's going to be 1, -3. It's going to go through here, isn't it? Right? And then the next one would be, normally would be 2, 8, right? The normal values are 1, 1, 2, 8, 3. This is the parent. X and Y. 3 would be 27. I'm not going to get that one on there, I don't think, because when this gets stretched by a factor of 3, the next point is going to be not at 8, but at 24. And can I fit 24 on there? Maybe 1, 2, 3, 5, 6, 7. Not quite. Down here somewhere. And 12, 15, 18, 21, 24. That one I can fit on right there. Right? And so there's this graph, this black graph is my parent function that has been flipped and stretched. Right? That's this function. Flipped and stretched. But what else do I need to do? I need to move it right and up, right? So right 3, so this point goes right 3 and up 3. Right 3, watch your scale, or watch my scale, I guess. Right 3 and up 3, I mean, that's going to be off my scale. It's going to be over here somewhere, I guess. And then right 3 and up 3, right 3 and up 3, and now I get my function there. And it's not beautiful, but oh well. And that's review, right? We've done this sort of, oh, that's supposed to be -3. Clean that up a bit. Okay, now we're asked to draw or put these calculations on this sketch. All right, dandy, I can do that. First of all, the A rock between 2 and 5. 2 is there. 5, uh-oh. 5's going to be down here, right? And so that's a secant, or supposed to be a secant, between 2 and 5. I'm going to make this go in both directions. Make it green. Dandy. And this, can I convince you that the slope of this secant is -9? Down 9, right 1. Yeah, looks like it's about -9. Now what about the tangent? Here the tangent's at 4. Tangent at 4. Get another different color here. At 4. Oh, there's that 0 that we were expecting. And the tangent is supposed to have a slope of -9. And could I convince you that that's supposed to be parallel to this green line? Maybe. Maybe. You know, I don't know if it would be, but that's not bad. It's not bad. But the idea here that we wanted to review is that, remember, the slope of a tangent is the instantaneous rate of change, and the average rate of change is the slope of the secant. So average rate of change, instantaneous rate of change. All right, we're going to pick up example 2 and 3 in part 2.